So I'm here to talk about this very exciting set of patterns, CQRS and event sourcing today. Are there any CQRS event sourcing experts in the room who already know everything and are going to criticize me every step of the way or anything? I don't know. Good, good. All right. So my name is Oliver Sturm. My email address is on here. We're going to skip everything else because we don't have time. My agenda today is to talk about these two patterns, as you might have guessed, and to explain to you why I think they're exciting, when you might be able to use them, and how you might possibly do this. So yeah, let's just get right into this. The consequence of both of these patterns is this thing called eventual consistency that I also hope to be able to talk about for a few minutes, perhaps, since that's a pretty interesting aspect of it. Now, looking at data access patterns, I have here a little piece of code which I believe is actually from an ASP.NET application. Not that it really matters, it is kind of meant to just illustrate the kind of process that you went through traditionally in a web application when you had pages that were displaying data and they might also be edited, right? So on page load, there is this little method of code there on init where a data object is basically retrieved, right? So we're talking on the server side. Maybe there are some PHP guys in the room. Server side is something you still do quite a bit in that area, isn't it? So on the server side, we would retrieve some kind of an object. I'm calling it the edit object up there. And we configure our page to display information from this edit object, right? In this case here by setting a data source property, but it doesn't really matter how you do it. The point is only that the rendered page will end up showing information from this object. Now let's say the page comes to the browser and the user goes and edits something in the page. There are some, text fields or something like that. They make edits and they submit the changed data. So as a result, I would then come into the second method as well, called page load, in which I'm testing whether the page is currently loaded as part of a post call, right? So in the situation that data has been submitted. And if that is the case, I will then take those changes that I have somehow fetched from the post data and merge them into my edit object, right? Like that. And then I save the edit object. So this is sort of a scenario that you would have found in similar sequence in very many applications that had some kind of server-side intelligence. Right? Of course, things might be different today. Perhaps you're talking about a web service that actually accepts changes from the client in order to persist those or whatever. But the mechanism in many cases is very similar, really. In many environments, people are very keen on systems like object relational mapping, clever data layers as a more general rule, perhaps, right? Data layers that allow us as developers to work against easy and intuitive APIs. And the data layer does a lot of the work that is required to persist our data back to the database, possibly do clever queries and all that kind of stuff, right? So this is the sort of round trip. Now, the thing about that is that, oh, well, here's a summary. Fair enough, I've given you that one. The thing about that is that in many cases, this approach is not entirely optimal, really, because we do some work that isn't actually always required. For a start, when the data is loaded in order to display on the page, in reality, you don't always actually require the same data when this happens, right? So there might be some pages in your application where, your customer or some very obvious object like that is actually displayed in its entirety, but there are probably few of those pages, right? A customer entity in some application can easily have, 50 or 100 fields associated. Other related data probably that comes in with it as well. And there are very few pages anywhere in your application, I'll bet you, that actually show all those fields at the same time, right? They really don't. At the same time, of course, the other way around, the same is true, if you will, which means that if you show information from a customer object, frequently it will actually be, it will include some extra data that is really retrieved from some other place, right? Like when your your persistence backend requires you to join data from various tables together, as an example, right? I don't know how many of you work with relational databases versus NoSQL databases, document databases, and so on, right? So your approaches obviously would vary depending on those parameters. But basically, the same remains true in many applications. The data storage, in terms of the entities that you define, the tables or collections that you use, and so on, is quite different from what is actually used in the application itself as far as the user can see, right? The information that the user can see is frequently retrieved from multiple locations, and at the same time, not all of it is often displayed at once. So from this idea, came the concept of CQRS. That's not a new concept. It's been around for probably 10 years or so. I don't know exactly, but yeah, it's quite old really by today's standards. The idea of it is to define separate execution paths for two different aspects of your application, and these aspects are commands and queries. The commands are the ones that are sent to the system when something actually happens, like, you know, an edit command or a command to create a new instance of something, right? For instance, these are commands. Commands could also be business processes, right? You can model your system along the lines of business processes. If your customer says, we have a process here where somebody places an order and they have to initially supply this and that and the other piece of information, and then after that we do some checking and we go back to them and then they confirm and they give us some extra detail, maybe the payment information is processed in a secondary step or something like that, right? So these are business processes, and frequently the commands in your system can, if you want to, adhere to these same lines, right? So that your business processes are directly modeled in your system. So these are commands, and the queries, quite obviously, are those processes that retrieve information for display or for any other purpose where the data is required. For example, data analysis processes, report generation, whatever they might be, right? So we realize, based on what I showed you initially, this kind of slightly old-fashioned data access sample, we realize that the processes of querying data and of performing commands are logically different, right? So we would benefit from keeping them separate on a technical level. And also, we realize that we work with different data models for those two scenarios. That means that the information that is being sent or received is not always the same, right? The information we actually require is not always the same. Frequently, there are actually multiple processes involved for sort of the same aspect. For instance, if you imagine you have a system where users can log in, then you would have a number of fields associated with each of these user objects in your system, and you would have processes to edit that information, but you will probably edit that information piece by piece, right? For example, maybe a user can easily go in and edit their own name if they like, right? Okay, that's no problem. But if they want to edit their email address, that's already a different process, because you may require the user to actually confirm their email address before the editing can take place, right? If you allow the user to change their password, that's an entirely different process again, right? And each of those processes has their own data model, if you like, because there are certain sets of information that are associated with each of the process, and only those will be passed instead of the entire user or whatever object in your system, right? So that's the idea of CQRS. One process can be different from another. We can save a lot of time, as it says up here, if we do this quite stringently. If page cycles are somehow required for operations in your system, depending on whatever technology platform you're working on, then you will basically be saving quite a lot of time by being able to keep these page cycles logically separate, right? You don't have to perform more work than is absolutely necessary in each case. It is also possible because it allows you to individually scale and generally treat your different execution paths. So the path that allows you to query data is different from the one for processing of commands, and as a result you can have individual services for it that scale up when query requests come in, lots of them, whereas the post commands might be fewer, right? You can do analyses on your system to find out what kind of characteristics you actually have. Most typical business applications do 90% querying, right? There are probably exceptions to that rule, but in general that is true. There might be applications that have specific bits somewhere where they do a lot of command processing. For example, if they do something like live data import or that kind of thing, right? In that case, they would receive a lot of commands. But these commands are also very specialized, right? They have a particular purpose in the system, and in general, the majority of the processes handled by the system would probably still be queries, right? So that's the characteristic, and viewing these execution paths separately, as it says in the last bullet there, means that you will maintain them separately, you can deploy them separately and handle their performance characteristics as needed. You can test them separately as well, right? Your overall application logic with the CQRS implementation gets easier. So here is an illustrative diagram to show you, how that might work in case you're a visual person. We've got the smiling client there on the left-hand side, and that client would then perhaps send a command to an entity that I'm calling a command engine down there at the bottom, right? So that's your command processor, and I've listed some possible names of commands in there: create customer, update customer, place order, like I said, yes. Each one of those would come with a certain associated set of values, right, that have to be passed along with that command. Now, the command engine would potentially access a database for storage purposes, right? I'm just giving this as an example here. Of course, in reality, the command could have any sort of other consequence inside your system. And on the other end of that, we have the query engine. So basically, the smiling client would also be able to submit a query to that query engine. For example, the information that is required in order to bring up an editing form for customer number 23, right? And then that information would be returned. We see up there Bob, right, is returned to the client, where the information can be displayed. And if somebody actually goes and changes Bob's details, then that would lead again to a command, update customer, being sent to the command engine. Right? That's the idea of separating those execution paths. And I have also listed that there might be a separate top customers query there, and I've put some arbitrary values in there just to illustrate that clearly the information returned by different types of queries could be entirely different. Right, that's an important idea in there, and it is like that all the way down to the query engine, right? So we don't have any point in this application, as it is depicted here, where we are working with any kind of a standard structure, a standard class type, perhaps, that always has exactly the same fields or anything like that, right? The models, the data models that are exchanged by each of the operations in here are different from each other, and they are specifically structured for whatever purpose that is that data model's purpose, right? So that's the idea of CQRS. Now, I think my next slide goes in that direction. You shouldn't necessarily imagine that your application structure has to be very complex or enormously scaled out or anything like that in order to use CQRS as a pattern, right? That's not really the intention. I was showing in the diagram how, we might have certain logical services or something, perhaps, if you will, in there for the command engine and the query engine, right? Of course you can imagine services if you're thinking using a microservices type of architecture, then perhaps we have services in there. I was mentioning individual scaling and all that stuff. But in reality, what the pattern is really about is mostly just the structural aspect of it, right? The assigning of responsibilities to those individual logical modules of your application. So you could do the same thing in a monolithic client application, if you like. Yeah, there is basically no limit to the to where this pattern could be applied. I personally don't think we hear, you know, typical criticism. Is it a complex pattern? I personally totally don't think so, because it really simplifies each individual piece of logic that your application implements somewhere. It simplifies it a lot compared to combined execution paths. Combined execution paths are usually more complex to begin with. You have to write more code to make sure that every time maybe a query runs or anything like that, you actually return precisely the right data, and you don't accidentally include stuff that might not really be included with that query, right? You have a difficult time making sure that based on user permissions and all kinds of other settings, perhaps the correct data is delivered and the incorrect data is not delivered, right? So that sort of thing is hard with combined execution paths. Easy to get wrong, hard to test sometimes. And with separate execution paths, this becomes much simpler. So in my experience, a CQRS application is actually structurally simpler. Using object relational mapping, some people are like really attached to that, which is why I have it in there. That is a system that is not really entirely compatible from a philosophical point of view with this whole separating execution paths thing, right? ORM was basically originally intended for the object-oriented programmers in various languages, Java among them right early on, who were trying to persist the complex object and class systems that they had previously already created, right? So it went from there, and today we have a lot of object relational mapping systems that kind of go the other way around, where people actually design databases in database servers, and then they have an object-oriented layer on top of it using some sort of an ORM tool. Potentially you could use this latter approach, if you really want to work with your data layer through the ORM, right? But in reality, the data persistence operations that we actually require are very simple. It depends on the kinds of clients and stuff that you use. But with most NoSQL databases, for example, the process of persisting some data in a format that would be easily usable here, and as we see also in event sourcing systems, that is usually quite simple to do, and you may not actually require any additional layer in between. That, of course, always has a certain degree of overhead, right? So that's to keep in mind. Right, so yep, enough said about that, I think. That's the when. Now, how do you do this? I think we've basically talked about most of these points, right? You model everything that happens as changes in your system as commands, so you have to try to gain an understanding of what your system actually does. What your users do, right? That's a very good starting point. Anything that your users do can be a command, basically, right? And there might be a few extra commands at some point, for example, for multi-step operations. If something has to happen later, then an extra command might be required for the later step, and so on, right? And then you can define your data models, which is usually quite simple because you basically just go by what is seen in the UI, right? That's what you need, basically. Of course, there are exceptions, like automated processing of certain data and so on, right? But as a starting point, that's a really good idea. It's a bit like defining view models in an MVVM pattern, right? Where, I mean, that's not hard because all you need to do is look at your screen and find out what the user actually needs to see there, right? That's your starting point. That's your 85% or something of what you need to do. And that's kind of similar in this scenario here as well. Okay. Let me check the time since we're running behind and everything. I think we're meant to finish at 11:15. Right, okay, that's not bad, that's not bad. So now the somewhat more complex topic really is the event sourcing topic. Event sourcing in itself is not necessarily directly connected to CQRS, but it does go hand in hand with the idea very easily, and you would basically always have separate execution paths in an event sourcing system. So that is why these two patterns are usually mentioned hand in hand, and it makes sense. Starting from the command idea right there, yeah, so we still send commands to the system in an event sourcing system. The biggest difference of it is really that the only persistence we have absolutely necessarily in an event sourcing system is the event store itself. Right? So that's the most important thing to realize, right? If you're thinking in terms of somebody familiar with relational databases, probably some NoSQL ones as well, where your database is basically the snapshot of all the information in your system right now, yeah? That is the old-fashioned mindset, if you will. My apologies, in comparison to this here, right? Because what we do in event sourcing is we don't store a snapshot of data. Well, in reality, we will in a moment, but just from the basic mindset. Yeah, the basic mindset is that instead of storing a snapshot of data as it is right now, what we do is we simply persist everything that happens in the system. So the commands, right? The commands are the entities that make things happen. The commands define what happens. You could begin, let's say, with an entirely empty data store, and then a command comes in, create customer, and you go and you create a customer object, right? A command comes in, update customer. You go and you change the object. Now, as long as you persist all the commands, and we do this in what is called an event log, I'll say more about that in a moment. As long as you persist all the commands, you could always begin again from your logical state 0, where you don't have any data in your application, and simply run through all the commands again, right? And you would then again arrive at the same state of the overall system today, right? So that is the idea. The event log is the only definitely available kind of persistence in an event sourcing system. And it is a pretty simple type of persistence because it's append only, right? So that can be handled very, very performantly. It's very fast, which is important. Theoretically, you could have multiple different processing services running in parallel, accepting commands as quickly as they possibly can, and converting them into events and appending them to the event log. Right? So that's kind of the idea with it. That is a very, very quick thing. Any state of any entity can be derived at any point in time from this log of events. Now, there is something happening basically in this, what I just call a conversion from the command to the event, right? So we begin with a command, and there is some kind of a service, I'll call it command processor, that accepts this command, and then it usually performs some basic validation on the command to make sure that it's valid from a very technical point of view, right? So the command will have to include the command name for a start. And for organization purposes, we also associate with each command the name of a so-called aggregate and the ID of such an aggregate. These are the typical 3 values that you expect a command to contain, at least, right? So the aggregate is like some sort of a logical unit, right? It doesn't necessarily have to correspond exactly to some sort of a domain entity or anything like that. In reality, some of the time it will. Yeah, so for example, if you go and create a new instance of something, then that will usually be the aggregate itself, right? And that also explains where the ID comes from, right? So you create customer and you pass in the name of, or rather your command would probably just be called create, and the aggregate name might be customer, And for the aggregate ID, the client normally specifies the aggregate ID for logical reasons. And that ID is expected to be unique, right? So the easiest way to do this is to work with UUIDs, but you can basically do that any way you want, right? So that information comes in from the outside. And at that point, the command processor is expected to perform some basic validation to find out whether it's okay to include this command or the event related to the command in the system's event log or not. Right? If the command processor says this is clearly incomplete, we don't have an aggregate name included here, then of course we never add it to the event log. Right? The validation can go further than that. It's a bit up to individual developers or teams how far you would like to take this. The idea is sort of that the command processor doesn't entirely care what the commands really say, right? So if you take validation very, very far, then of course you will have to be changing your command processor all the time as you add new aggregate commands and stuff like that into your system, right? So there's a compromise somewhere in between. Don't validate more than necessary, basically. The aggregates I've been talking about are basically little objects that are, in some implementations, they're kept in memory the entire time. In some implementations, they might be retrieved from a shared cache or something along these lines. Sometimes people also, for optimization purposes, use snapshots, as I say down there. So when the event log, of course, over time reaches a pretty large number of rows, then they basically create a snapshot of the aggregate state at various points in time, perhaps, you know, every 50,000 commands or once a day or something like that. And then, of course, a particular aggregate state might be loaded from that persistent snapshot, right? So that's where your aggregate comes from. But the aggregate is not an object that represents the entire state of some entity, like, for example, a customer with all those 100 fields I was talking about, right? But the aggregate only contains whatever very few fields are required for validation purposes. So for a start, you might want to be able to figure out whether an object with a certain ID has actually been created before, right? So if somebody does like create customer number 1 and then they do exactly the same again afterwards, it would be nice to be able to tell them on the second run that that thing already exists, right? So that's one very simple flag that is usually included with an aggregate. Do we have this object already, right? That kind of thing. So this validation, it's what's meant to be supported by the aggregates. It doesn't go any further than that. So aggregates are very small. They can, for performance purposes, be persisted in snapshots, and they will otherwise be retrieved by running through the events in the event log and performing certain changes. And these changes are called projections, in case you were wondering why that term is on there. So when an event is basically interpreted and certain changes are made to the aggregate, and in a moment I'll talk about read models as well, that is called a projection, right? So that's the idea there. Okay. Now, this is the basic idea of event sourcing. I have talked about this, I think, now in parts here. We can, using the events, we can find out at any point in time what the system actually does, right? Clearly, this method of data storage is much more powerful in a way than the method of storing a particular snapshot of data the entire time, right? In an event sourcing system, we know what happened in the entire system in all time, right? Back to whenever it was first installed, not just what the state of data is today. So clearly there's much more in that. Of course, we also have various pieces of tracking functionality in most traditional applications, right? Depending on the industry you work in, you might have to have auditing of certain object operations or entity operations, whatever, in your application anyway, and event sourcing covers all these aspects at the same time, right? An important thing is that the consequences of an event in your overall system are actually not set in stone. I haven't talked about read models yet. I will in a moment. Read models, just in a nutshell, are basically the query part of your application where a client retrieves information from, right? And these read models are basically data storage elements that are derived from the event stream. So whenever events come through the system, the read model might be changed in some way, or maybe not, right? Depending whether the event has anything to do with the data in that particular read model, right? If there's a connection, a change might be made. If not, then not, right? So, and that's the way it works. But this isn't something that can easily be changed later on. If you decide that you have a read model that was originally created to support, you know, some kind of a report, maybe, so there are like 10 fields in the read model at the moment and they appear in a report, and now the customer comes and says, oh yeah, we would actually like to have, you know, another field in there, and how about we do some clever total calculation or something underneath? Then you basically just go and change the projection code of your read model, the code that transfers the event information into your read model storage somehow. And then you go and kill the existing database of the read model. You just go and drop all the old state, and you replay, and that's an important concept, you replay the event store for this read model, which means that the read model basically goes through the events all the way along to its current state. And then all of a sudden you have a completely changed and possibly different structure of data to what you had before. It's also very powerful in development, right? We've all seen that where if you work with snapshot databases, the traditional way, sometimes you stumble into issues where all of a sudden a particular field in your database, or maybe the output on screen, you know, that a customer reports to you, is not what you expect it to be, right? And then you trace it and you find, oh yeah, well, there's a value in the database that's actually wrong. But the problem is you have no idea how that got there in the first place, right? You even don't know when it got there in the first place. You might be able to look at some old backups to find, you know, when did this first creep in or something. But then that's often the end of the story, you know, because you don't know the state of everything else in the system at that precise point in time. And there are frequently some pretty severe limits to how much you can debug on that basis, right? Well, in an event sourcing system, the data that is in your read modules is only derived from the event store, and as a result, you can recreate it at any point in time you like. You can work from a backup, of course, if you like, so you don't always have to replay the entire event store, right? You might be able to work from some sort of a persistent state where the read model was still intact, right, perhaps. And as a result, you have a much more stable and extensible system in that. Okay, now let's see. I think I have a diagram in here, and this kind of drives home the whole points about the read models that I've only made partially so far. So those of you in my workshop yesterday have already seen this fantastic result of my drawing skills, okay? So in this case here, we've got the smiling client at the top right there. In actual fact, I've also included a web server there on the left-hand side. I think the picture looks sort of a bit grainy. I must be running a funny resolution or something. I hope you are mostly able to see what I'm trying to explain here. So the client is in the middle at the top. It accesses a web application, perhaps from a web server, perhaps some other way, right? The web application might be deployed to the client through an app store or something like that, of course. It doesn't really matter how the application gets to the client. And now the client can send commands to this cloud thing down here in the bottom left corner, right? That is the command processor. That's what it says in there in case somebody in the back can't read it. Command processor, cloud in the bottom left, okay? So that's the thing that we've already talked about. The command processor takes the command, performs a bit of validation, puts it in the event store, and then, and this is the part we haven't mentioned so far, the command processor also goes and publishes the event that has been created as a result of the command to the rest of the system. It just kind of throws it up in the air, yeah? mostly it's done that way at least. Of course, you could be more dedicated to who you send it to or that kind of thing, but in reality, most of the time, it's perfectly fine to just put it out to everybody. And in the middle there, you see, I've put this message queue or event bus hub thing in there, right? It totally doesn't matter. It's a logical thing, right? It's just meant to say we have some kind of a communications bus at this point. So if the event has been published by the command processor, the idea is that the other remaining entities, there are 3 of them here as an example, the other cloudy bits, yeah, they could, if they wanted to, receive those events and then, of course, react to them in some way. And this is the role of the read models in your system, right? So the read models are basically services in their own right. Sometimes you might combine them, so you have one service that takes care of running several individual read models perhaps, right? So that's again not set in stone, but you have individual responsible entities in there, and their responsibility is to receive events, usually do some sort of filtering on the events. In other words, they find out which of the events are actually relevant, you know, to the task at hand. And then the read model performs some kind of persistence, usually, right, in order to remember some of the information. Just that information which is relevant to the job. Right? So if you have a read model that is made for the handling of your customer data, since we've been talking about these examples with customers a lot here, then you would probably have some kind of read model that returns an overview of the customers that are already in your system. Such overviews will mostly have a limited set of fields, right? You probably don't need all the many that you have in your system in that overview. There might be some read models for the purpose of editing the customers. Possibly there's more than one mode of editing. A customer might be able to go into the system, him or herself, to edit their own data. And on the other hand, there might be back office employees who can also edit the customer, but their view is not exactly the same as the customers, right? So there might be different ones. And that's what they combine. So that is why each of those clouds in the picture right there have their own DB symbol, database, storage in other words, right? So each of those services stores its own snapshot of whatever current information it has for its own purposes. Finally, the client, I haven't mentioned that so far, there are several black arrows saying load data. The client will be able to load information from these different read models, right? Of course, the client will always kind of have to know how to contact the read models and so on, right? So this is not a technical diagram. You might have some extra infrastructure in between, perhaps some sort of a proxy service that allows the client to easily contact any one of the read models by name or something instead of having to use their IP addresses. In some systems, you may actually have different communication channels, so it's easy enough to imagine the endpoints to work through HTTP, right? But at the same time, maybe you would also like other access points for internal use, like the ability to contact a read model through the message queue, as an example, right? Or whichever way you want, really. So again, this is not a technical diagram, it's more of a logical diagram, the different communication paths that we have, yeah? So that's the idea. We've got the command processor for the command part, we've got the read models for the read part, and we've got this event coordinated system for data pass through in the middle of it. Now, using the example from my workshop yesterday, I'm going to illustrate that to you as well. Let me just see here, because I'm not sure if we've got a good resolution for me to be showing this. Hang on, well, this is now not entirely the right thing anyway. Sorry, that was probably because I didn't get round to doing it previously due to the oh, right, okay. That's fine then. Let's just use this one. Due to the display issues that we had, I was going to say. Okay, so can you guys more or less read the code that is coming up here? In the back, is it too small? Okay, I see thumbs up. That's excellent. Okay, right. So, well, I don't actually know if we're going to have a look at much of this code now that I think about it. What I mainly want to look at really is what happens here in the system. So let me bring up some logs here. These are the logs of the running system, or they should be at least. Nothing's happening. Oh, right. Oh, fair enough. That's interesting. The system isn't actually running anyway. Fantastic. There's nothing like a few things going wrong. So let's kill this again. I can also, while I'm at it, go to the correct project that I was actually going to use. And now I'm realizing that probably I forgot in all the hassle that I need to run a MongoDB instance in the background here and start the project again. Okay, yeah. Now the front-end application is a React one. It usually takes a little while on my little Chromebook here to actually come up, so we'll have to wait for that. That's why I started it before we began here, but that didn't help clearly. So okay, let's see. Here we've got the application, hopefully. Oh yeah, okay, presentation. Appears to be something wrong though, but I don't think it's actually started even, has it? Starting the development server. No, I don't think it's really started. I think this is just the browser having some fun there with yesterday's cached version or something like that. The React development server takes quite an impressively long time on my little Chromebook here to come up. I don't know why really, because it is reasonably fast almost all the time otherwise. But this development server takes a long time. Well, it should be there any moment now. Somebody know a joke, maybe? No? Come on now. You can make a JavaScript joke if you like, yes, absolutely. Oh, here we are. Okay, finally. Right, excellent. So this should bring up the actual application now. There we go. There isn't any data in it right at the moment because I restarted my Docker Mongo image that I was running locally here yesterday. Now, this is a very simple thing, really. There are two views in this application here to show me customers and their orders, right? Nothing much exciting in there. And we're not going to go into this in great detail. I've got a link on my slides for you guys to look at the demo yourself if you like. However, the point at this stage really is only what we see in here. Now, let me try to make this a bit bigger here. Why is it not making it bigger? What am I doing wrong now? Ah, here we go, bigger, right? So can you see the text in the log window, I suppose? Yeah, okay, more thumbs up, fantastic. So the point of the whole exercise is I will trigger an operation in here through my front-end application, okay? So I call this Ollie, which I always do because that's me, and I live in Scotland, so I'll just enter that. And now I hit save, and then we can see what happens in the back end as a result. Yeah, here we are. I'm back in the list view right now, and this is just a demo thing, so it only shows me the newly created ID and my own name here. And we can now see in the log window here what actually happened in the background. Now let me see where this begins. It begins here, where it says, a service called command processor in my system has received a command. This is the command that came in. I've described this to you before, right? So here it is now. It says we have an aggregate name, customer. We have an aggregate ID. This is just a newly generated UUID value that has been associated. And we have a command. The command is called create. And then there is a payload, and the payload basically has all the details that I entered. So in this case, you know, my location and name information. Now, as a result of this, the command processor generates an event. Here it is. And that event is almost the same, just with a slightly different structure, really, as the command. That is quite common, really. As long as your validation succeeds, your events will usually be quite similar to the commands. Okay, and then what happens is we publish the event here, which means that it is basically sent to the communications bus. Here in my system, that is based on 0MQ as a message queue, but could be anything like that. And then here we have the read model, or one of them. There are actually two read models. This one is the first one, called orders, that says we have received this message with the event. And the customer's read model comes along shortly afterwards and has also received this thing. And then we're projecting these events to particular read models, right? So the customer's read model service here actually encapsulates two separate read models called overview and editing. And both of them have an interest in this particular event customer created, right? Not every read model in your system, of course, will actually be interested in an event about creation of customers, right? So you have to distinguish that. And only the ones that have handlers for this particular event will then be called for projection. And here it says we're projecting those events. This is the end of the commands. Yeah, there's a bit more in here because I've also got automatic change notification in the system here and that kind of stuff. I'm not going to go into that, but you can feel free to check that out if you like. Right, so this is the sequence that I was describing. I could also show you just quickly, let's do docker ps. If I'm doing docker exec and go in there. Now, what's my number here? That will be 38, I think. Here we go. So now I'm in Mongo, show databases. We've got the read model and the event databases and everything in there. So if I do use events and then we do db events find even. I can't type find, as it turns out. There we go. So this is the event, just one of them, that has made it into my event store. And there's a separate database. I mean, of course, now I'm doing CD. Yeah, that makes sense. Of course, you know, since we're on a development machine, I'm basically running all the processes against the same database server, right? In reality, they might be separate, of course. But at least I'm using separate databases, so it is as close as it could be really to the real thing right there. Okay, so now we have the overview read model, which is the one that we also see in the UI, right? Overview, and here's that one piece of information for Ollie. You might note that the overview read model does not contain the location, right? I decided to leave it out just as an example, okay? So there is actually information associated with the user that is not part of the overview read model. But there's a separate read model for editing. So if I do db editing find, you will see that in there, that location is included, right? So for editing purposes, if I'm going to edit this user Ollie, here's the Scotland that I entered, right? But it is not part of the overview read model. I mean, this is only an example, but it's a very common scenario that you have different read models for these different purposes of showing data versus editing it, possibly showing it in different ways, and so on. Okay? All right, we've got 5 minutes to go, so we must continue with a few final words here. Well, I have a few words on when to use event sourcing. I am mentioning in there that, of course, event sourcing does have a certain complexity. It is actually a complexity, in my experience, that is very easy and actually a lot of fun to get used to. Right? So I'm not going to say that the complexity should be a reason to not consider event sourcing almost anywhere. I personally think that the upsides of this model are great, right? Even for a developer trying to analyze your own system while you develop it, finding issues with it, tracking down behavioral problems, making extensions after the fact, and all that kind of stuff comes very easily in an event sourcing system. So there is complexity with the messages, the commands you send, the events, and so on. That's a bit of an architectural complexity, perhaps, but that's not really hard to manage, and it is very worthwhile. So for those reasons, I would generally suggest checking out event sourcing as a pattern. I think that is generally a good recommendation. Of course, there are perhaps scenarios, highly monolithic applications where you really just don't care about the aspects of possibly scaling individual bits of your application and all that kind of stuff. But even then, you can still benefit from the developer advantages as well, and the maintenance advantages that you gain in the longer term. So that's a good idea. Now, okay, I think the how, we have really seen most of it because of that diagram I showed you. I don't think there is anything much more in there. I do recommend using existing libraries, of course. Oh, I think this was out of place in here, I'm afraid. Here we go. And the one item that I would like to talk a bit about in the last few minutes we have, unfortunately, is eventual consistency. I was meaning to possibly have a little more time for that. Basically, the eventual consistency is what automatically happens in the system that I've described here with event sourcing, for the simple reason that there is a split, even in CQRS by itself, not just with event sourcing even, there is a split in your timeline between the point a command is sent to the command processor and the point in time where a read model potentially reflects the related updates, right? That is logically the case, and this is entirely separate, and of course it is meant to be separate, right? It is meant to be decoupled and everything, so you couldn't easily drop some kind of distributed transaction system on top of it in order to gain strong consistency. Then you would also lose all the advantages of it, right? So eventual consistency is a logical consequence. And I always like to stress for the Germans, of course, that eventual does not mean eventuell. Okay? Eventual means letztendlich. So that doesn't mean maybe it's consistent and maybe it isn't, right? Like some people like to joke, I know that, but it means in the end it'll be consistent. And this is actually a system that you find in real life quite a lot. I personally like some examples about it. For instance, the Starbucks analogy, right? Where you walk into Starbucks to order a coffee and they actually ask you before you're even at the counter what coffee you want, and they pass it around between 5 different people, you know, those barista people at the coffee machine and all that kind of stuff. And when you come to the checkout desk, you pay for a coffee, but it's not necessarily the one you actually ordered in the first place, right? And then you go to wait for your coffee at the end of the line, and you pick up a coffee, and if you don't like it, you just pour it over the guy's head and make him make you a new one, right? And that's not exactly the coffee you might have ordered or paid for, right? Because Starbucks basically guarantees that you walk out of the place happy, right? That's the idea. They want you to walk away happy with the product you received, and they want, of course, to receive some money for it, but it's clearly not very important to them that that is actually the money precisely for the product you walked out of the shop with, right? That's eventual consistency. What they sell is customer happiness, right? Basically, that's it. And that is eventual consistency. It is achieved by means of equalizing transactions. So if something goes wrong in this chain, let's say, you know, you're not actually trying to mistreat the process, but you are just trying to get your coffee, in that case, things could go wrong. Somebody could pass on the wrong information, perhaps, whatever. And they make good on that by simply apologizing to you and giving you an extra product, if you like, right? That kind of thing. So they equalize. And that's exactly what happens elsewhere as well. If you order something at Amazon and it turns out they don't happen to have the product in the end, then they might end up apologizing and giving you a voucher or something, perhaps, you know, that kind of thing. So these mechanisms are used. And unfortunately, we're running out of time. I can recommend to you, that's not my fault today that we're running over, that's new. I've got this little diagram in here for the CAP theorem, which kind of goes hand in hand with this idea that you can't always achieve all the different criteria of persistence systems that you would like to see. So I recommend you check this out in some detail. And hang on, there should be a link here somewhere. Oh yeah, the one here at the bottom is an interesting study, but it reads quite fluently. It's an interesting study on the idea of eventual consistency, and there are some other examples in there for where eventual consistency is actually used in everyday life and in computer systems, and even in those computer systems where you think we really need strong consistency, right? Like whatever in banking or whatever, as an example. They use eventual consistency all the time in banking. So there's a lot more information there. Unfortunately, due to our technical problems, we didn't have those extra 5 or 10 minutes, so I will call it a day at this point. This is the source of the presentation here, if you'd like to have a look at the slides yourself. And the complete demo code of the sample I was showing you is available as well online. And that's me done then. Oh, I'll let you take your pictures there. Fair enough. Thank you very much for being here, and I hope you have a great conference. Thank you.